and welcome to this new class. And in this class we are going to start the new topic, which is it's the canonical transformations. So in general, you have started from this Lagrangian formalism, that is depending upon this generalized coordinate, generalized velocity and time, and then we transform that into the Hamiltonian formulas. That you what you do in transformation, that your generalized velocity is transformed into the generalized momenta. Okay, that is how you transform Lagrangian to Hamiltonian through a transformation relation. If you remember that this is H is going to some PQ dot minus your Lagrangian. This is what the transformation equation is. But that transformation was related to that in important in terms of that you are going to ease your mathematical calculation from this second order linear differential equation to these two first order linear differential equation. So actually, what is the number of n differential equation you are going to have in Lagrangian to solve? Those were second order ordinary differential equation. But in Hamiltonian, the number of equations were getting doubled from n to 2n, but those were this single first order ordinary differential equation. So that in that way the mathematical calculation become easy to this transformation of Lagrangian formulas to Hamiltonian formulas. Okay. Now, but the problem is that only in a situation when this your Hamiltonian is a constant of motion. Okay, so and where all the coordinates qi are cyclic. So when in your Hamiltonian this qr, the coordinate is going to be cyclic, then you know that the corresponding generalized momenta corresponding to that particular generalized coordinate which is cyclic, that momenta is going to be constant. This is we know that this pi corresponding to that generalized momenta. If my Lagrange Hamiltonian is depending upon is not depending, that is theta dot or p theta we have. So if it is it's theta is a cyclic, if theta is cyclic, then we know that the p theta, the momentum corresponding to this cyclic coordinate which is absent from the Hamiltonian, this is going to be a constant. Okay, so this is going to be constant. And if you remember the Hamilton equations of motions, then you know that these are in terms of Hamiltonian. So this is going to be constant because this is a constant quantity if you consider it is some constant alpha. Okay, so since the Hamiltonian is a constant of motion and it is the coordinates are cyclic, so therefore this equation what I can write is H is depending upon all the alphas. These are basically the conjugate momenta which are going to be constant of motion. That means the Hamiltonian is depending on all these momenta which are actually going to be constant. And the Hamiltonian's equation for motion, that is q dot is delta H upon delta pi. If you remember the Hamilton equations of motions, that is minus pi dot is going to be delta H upon delta q, and then this is qi dot is delta H upon delta pi. So if you calculate delta H upon delta pi q dot, that is in terms of pi. So all these pi, you know that these pi's are going to be constant because the corresponding generalized coordinate is absent from the Hamiltonian. These are cyclic. So if I differentiating with respect to this, so that means I am differentiating with respect to some constant, that is always going to be, if whatever it is going to be the function of that constant. Okay, so in that sense my generalized velocity q dot is going to be a function of that constant. If I have this dq by dt, that is my q dot is my omega, okay, omega I, which is a constant depending upon this alpha. So if I differentiate it, so this dq differentiated, that is omega I and dt. So if this is going to be some q and then omega t and some plus constant of integration. Okay, so betas I are the constant of integration that is determined by some initial conditions depending upon what kind of problems you are solving. So in general, what we do consider is that the transformation which involves going from one set of coordinate qi to a new set qq by transformation equation of the form, if qi is going to some q, that is going to qq, which depends upon qqt. But before that, going to transformation, let me tell you that uh, okay, so one thing is clear, that solving a mechanical problem, your life becomes simple that when you transform from Lagrangian to Hamiltonian. So please take it note that when you transform from Lagrangian to Hamiltonian, and if your Hamiltonian is time independent and you have a corresponding cyclic coordinate in that Hamiltonian, so that corresponding to that cyclic coordinate, your conjugate momenta is going to be, or generalized momenta is going to be constant of motion. Then your equation, Hamilton equation of motion, this is going to give you a simpler life, because then solving this is become very easy. So when your Hamiltonian is having some cyclic coordinate and the corresponding momenta is going to be constant, then the solution becomes very easy. This is one important factor which has to be considered during the canonical transformation. So so in this transformation, what we do is that we try to transform our old coordinate, which are my small q and small p, to some new coordinate, capital Q and capital P, and they are intertransferable. That is, my if I write can new coordinate qi, this qi is can be written in terms of the old q, and then similarly one is missing. Similarly, we can write my pi. This is going to be my pi can be written in terms of my small old p. Okay, so this is what we have. But we know already these are transferable. Q in terms of a small q, and I can write a small q in terms of the capital Q. Similarly for phi, you know that this is, I can write this, this is my small q going in terms of this capital Q, r and theta. Okay, in terms of the capital Q, or so this is my small p, say, and this is going to be, say for example, this is going to be in terms of the capital P and Q's. Okay, capital P's and Q's. So what I can write is and then you write this is r in terms of r. You can write r, then you write this r is your r in terms of x and y. You know the relation. Okay, so this is r equal to x square plus y square, and then this relation, you know. So this is just to see that the transformation is feasible, and such transformation are known as the point transformation of configuration space. That what we are talking about is like transformation from a small qp to capital QP some QP. Okay, so these Q and P are my generalized coordinates. So when generalized coordinate, we talk about generalized coordinate, these are always in the configuration space. So whatever I am doing the transformation, this is always in the configuration space. So this small qp to qp transformation is point transformation. It's a point transformation in the configuration space. Okay, so I'm transforming, like, you know, this if one point in the configuration space is defining the configuration of a system as a whole. So in Hamiltonian formulas, the conjugate momenta are also independent variable as generalized coordinate. Okay, because when you write the Lagrangian, that is q and p and t, this is in Lagrangian depends upon q dot and t. So q is generalized coordinate, which are all independent, and in Hamiltonian, when you transform Hamiltonian, so this q and this generalized velocity transform into the momenta. So q and p are, these q and p in the Hamiltonian are basically independent variable as generalized coordinates. So therefore we need a more general type of transformation that involves both generalized coordinate and the corresponding conjugate momenta. Okay, so if I transform my q to a small q to a capital Q, and and correspondingly that momenta is getting transformed from small p to capital P, then what is going to be the advantage that if the equations of motion are simpler in the new set of QP than in the original QP, okay, then this is going to be advantage. Second thing, if all the coordinates are made cyclic by transformation, the solution will be simpler. So what you demand that if you transform a small q to capital Q, and because Q and P are totally independent, so if it's correspondingly P, if my transformation also give my small p to capital P, such that so that if you transform such new old coordinate to new coordinate, so then your equations are going to be simpler. And in the additional advantage is that if your transformation is such that you made that generalized coordinate, this Q is as a cyclic coordinate, this capital Q as a cyclic coordinate. Okay, so then you know that when there is a cyclic coordinate in the Hamiltonian, then your equations are going to be simple to solve. Okay, so this the transformation, the such kinds of transformation from QP to small qp to capital QP with invertible situation, that I can transform from capital QP to a small qp. The equation of transformations are the point transformation of the phase space. Okay, so that transformation, when you do this q to capital Q, this is the point transformation in configuration space. Okay, and when you add momentum to that, that is the configuration transformation in the phase space, because phase space is energy space and momentum you consider. Okay, so you know that point transformation is configuration space, that you are doing your transformation from old coordinate to new coordinate, and then you can also do from new coordinate to old coordinate, that is transforming point from one space to the other in within configuration space. And then if you add the momentum transfer correspondingly related to that, then this is going to be point transformation in phase space. Okay, so what is canonical transformation? So is in Hamiltonian mechanics, basically a canonical transformation means now you're going to change the variable, okay, from one set of generalized coordinate and momenta QIPI, this QIPIs, to another set, new set, which is say capital Q and PI. But condition is that preserve the form of the Hamilton's equation. Okay, so and then the second thing is a canonical transformation is transform that keeps the physics same but changes the mathematical description actually. So it's like changing the coordinate in a way that a Hamiltonian structure of the system remains intact. That is what is demanding, and that can be done that is helpful in, like, if your Hamiltonian is cyclic in some coordinates. Okay, so the QP set obeys, like we old coordinate QPs obeys the Hamiltonian equation, that is Q dot is equal to delta H upon delta Pi, and P dot is delta H upon delta Qi. Okay, and satisfy the Hamilton's modified principle that Pi Qi, that is variation from the original path, is going to be always zero. Okay, earlier Hamilton principle says that this integral from t1 to t2, your Lagrangian q dot t dt, that is delta I is going to be 0. But when you transform from Lagrangian to Hamiltonian, then this is known as the modified Hamilton principle, and that is, so my old coordinate Q and P are going to obey the Hamilton canonical equations, and going to satisfy the modified Hamilton principle. So what we are interested that so such kind of transformation from old coordinate to the new coordinate, these are QP, such that they follow the same type of Hamilton's canonical equations. That is, if my transforming from QP to some QP, then my Hamiltonian, say new Hamiltonian is K. So this is Q dot is delta K by Pi. If you take the analogy from here, and this Pi dot is going to be minus delta K upon delta Qi, and it also is going to specify the same Hamilton canonical equation, that is going to have Pi Qi dot minus H depending upon Q, P and T. So this is also going to satisfy the modified Hamilton principle as always. Okay. So both these conditions, that is going to the new coordinate is going to satisfy the Hamilton's canonical equation, and the modified Hamilton principle is for the canonical transformation of this old coordinate to, or such this kind of transformation is known as the canonical transformation. The basic funda into transforming is this, that try to make through a transformation into the new coordinate system, into the new coordinate, such that you make this new generalized coordinate to be cyclic in Hamiltonian. Okay. So since the general form of modified Hamiltonian principle has zero variation, because this we know that delta is going to be has to be zero. So at the end points, because if you remember that when you do from point 1 to point 2, if a system is moving from point 1 to point 2, and this is whatever the deviation from path, so this is my actual path, but at these end points, whatever the variation, and this is going to be zero. Okay. So both statement will satisfy if the integrand are connected by a relation of the form, because this is the modified Hamiltonian in old coordinate, this is in QP, and this is in new coordinate, that is capital Q and capital P. So if they are going to satisfy this equal to zero, then we can perform a transformation such that we've multiplied by some lambda multiplicative constant, and the new Hamiltonian, if we add some function, time derivative of function in phase space coordinate, which is a continuous second order derivative. And if you remember that we have done the calculation that in the Hamiltonian or Lagrangian, if you add a component that is the total time derivative of a function, and that function is first and second order of derivative of that function is going to be continuous, then the Hamiltonian and Lagrangian is not going to be transformed, that this remains invariant. So with this kind of mathematical transformation, that if I multiply with lambda, this is a multiplicative constant which is independent of the canonical coordinate and time, that is lambda is not going to depend upon lambda q p and t. It's not going to depend upon q p and time, it's just a multiplicative constant, but this f is going to depend upon this. Okay. So it can depends upon mixed q original coordinate and as well as the new coordinate. So when this, if you do such kind of simple transformation involving a multiplicative constant, this such type of transformation are known as the scale transformation, because you are multiplying by a certain constant, certain scale, you are scaling to make them equal. So that is known as the scale transformation. But the last term in this equation, that is delta f by delta t. Okay, so this last term contribute to the variation of the action integral, but only at the end point. So for that we demand that variation has to be zero at end points at t1 and t2. Okay, that is demanded, and that f can be function of qpt and can function of old coordinate as well as a new coordinate, but lambda was just a multiplicative constant. Okay, so that was the scale transformation. And second demand is that variation of that term which you add, time derivative of that function f, that is going to vanish at the endpoints, and because you had to follow the modified Hamilton transformation equation. So if you put lambda equal to 1, okay, the transformation between the two sets of canonical coordinates qp and qp will satisfy. But now with lambda is equal to 1, what I have is this thing. So if you take lambda is equal to 1, that is the canonical transformation. But if lambda is not equal to 1, then that will be extended canonical transformation. So for now we are considering that the case where lambda equal to 1, that is a simple scale transformation, and under the canonical transformation of new coordinate to the old coordinate. So that transformation will be governed by this equation, that this part, this modified Hamilton equations of motion in the old coordinate is equal to the modified Hamilton equation in this new coordinate plus some time derivative of a function which is going to satisfy at endpoints and can be a function of both the old as well as new coordinates. Okay, so this is important. And let's have this is written here. So now on the left hand side of this equation, we have a function of original coordinates, a small q, a small p, and a small t, and the first two terms on the right hand side depends upon capital P and capital Q. So hence the transformation that we are not including right now, this transforming this to this from qp t to qpt. Okay, so this is what is being transformed, and their inverse, we can do the inverse also. So therefore if this is going to happen, so this the third, this term on the right hand side must be a function of original qp and a new variable qp. Okay, and then can have a mix of that in order to uh, uh, transformation to be effective. And this basically this term add as a bridge to equate the transformation from this old coordinate to new coordinate and new coordinate to old coordinate. So these f's are these f's are going to have, because they depends upon the combination of old and new coordinates. So there we are going to have the four option for that f, that uh, we have t is there, we have q, and we have p. So I have old coordinates small q, small p, and I have new coordinate capital Q and capital P. So what combination we can make? It can depends upon q. This is q, and then I can have a small q and a small p. So I have small q and capital P, and then can have v with this small p q and a small p capital P, a small p capital Q, a small p capital Q. There's no other combination. The four combinations are there through which we can have such kind of transformation. So that's why this is acting as a bridge to between the transformation from old coordinate to new coordinate and new coordinate to old coordinates. So this is known as the generating function of the transformation. Okay, so we have to figure out what are the uh, generating functions of these transformations. This is so let us try to figure out what is the first generating function, the type 1. So these four are known as this is type 1, type 2, type 3, and type 4. There are four type of generating functions. So type 1 is which depending upon a small q, capital Q and T. So and from equation 4, this is my equation 4. So we can have because f is now my function of this QT. So I can write df by dt because f depends upon q. So f with respect to t, and f with respect to q, f with respect to q, and this is what this is delta q by delta t because we are doing dt, and then f with respect to capital Q, and then delta q by delta t, that is my q dot. Okay, now you see that if I multiply by dt and both sides, so what I can have because this is you have pi, this is going to have delta q by delta t plus or minus h. So if I multiply by dt, so this dt will cancel out, so I have dq, so they have pi dq. Okay, and then similarly this is my delta q by delta t. So if I multiply by dt, so this is dq by dt, so this will cancel out, so I have dq. So this is pq dot, you have dq. So you have So I can write these equations as basically I can write these equations as so let me write this as this term is sum over I. This is p dq minus h, and this is going to be capital P dq, and then I have k here, and then what is this thing is delta f1 by delta t, and this is delta f1 by delta qi, and this is dq, and plus delta f1 by delta q, and this is dq. Okay, so now we are trying to find what is a small dq, and then I have a small dq. So if I take this together, this is a small dq, that is pi with this, and this is delta f upon delta qi, but because this is on the right hand side, if you go this side, this is becomes minus. So I have one term, that is pi minus delta f upon delta q with delta qi. Similarly, I'm going to figure out what is dq terms. So dq, we have pi, capital Pi, and then the capital dq is here, so that is delta f upon delta qi. So this is one term, and then the rest of the term is like the new Hamiltonian is my k. So this becomes say if I take this side on the right side, on the left side, so this become with h, this is k minus h, and this time derivative also go to the left side, that becomes delta ft. So these are all equal to 0. So since these are old coordinates, these are the new coordinates, so a dt is also there. So since these are q, this is q are all independent coordinates, so dq and dqr are also going to be independent coordinates. So because they are independent, so I can equate the coefficient of these dq and capital dq going to be 0. So if I equate these equal to 0, this equal to 0, and this equal to 0, so what I'm going to get is relation that a small pi is you see that a small pi equal to delta f upon delta q. So this is small pi is delta f1 upon delta q, and then similarly capital pi and then capital q. Okay, so my f1, my first generating function, was depending upon this small q and capital Q and t. So this is written here, a small q, capital Q and t, and this is for all three relations. So what we are going to get from these relations? So if you see if this first relation, equation number 5, so what I'm going to get is from equation number 5, this is going to give me, if I solve this differential, what I'm going to get is capital Q in terms of the small q, small p and t. Okay, so if I solve this, that is, this is pi is delta f1, this is going to be depending upon q and t, and if I with respect to q, so if I differentiate with respect to q, capital Q in terms of q, p and t, and then if you see this equation, so what I'm going to get is pi is minus delta f1, this is going to q and t, and this is delta qi. Okay, so what I'm going to get is I'm differentiating with respect to capital qi. So what I'm going to get is, like, if I'm going to get capital P in terms of the q, small q, small p and t. Okay, so why I'm writing, because we need a small q and a small p in terms of qpt. Okay, so here from equation 6, okay, from equation 6, what you're going to get is qp and t. Okay, from this q, and then from these equations, these two equations, if you uh, get rid of this q from these equations, so what you're getting is capital P here. Okay, so let me again try to make you clear that what you're going to do is from first equation, what I'm going to get is capital Q in terms of small q, a small p, a small t. Okay, so I'm going to differentiate it. Just like I'm going to have a q is relation between like q, which is depending on q, p and t, a relation between q, p and t. Okay, and then from this equation I'm going to get a relation between the q, which is in capital small q, small t, and capital P, small q, capital P, and T. Okay, so now I can I can eliminate this small q, so get this capital P. So this capital P will be, now if I eliminate this capital Q, so this will be in a small q, that is small p and small t. So this is what I want, that the transformation from a small qpt to capital Q, a small qpt the capital P. So from this these transformations equation, all these transformation equations, now I'm going to get my what is the transformation equations, and that these are possible from the generator equation. So once you have a generator, then you can generate the transformation equation, that is going to be the canonical. Or other way, if your transformation is given to you, then you can find what kind of generator is there, and then you can find what is this transformation is canonical or not. That we were going to discuss it. Okay, so so now you know that my first generator equation, which depends upon a small q, capital Q, and T, is going to give me these are the transformation equations which are going to give me the canonical way of transforming old coordinate to the new coordinate. And if the second type of generating function, which depends upon a small q, capital P, and T, if I'm going to put it here, what I'm going to get is you see that in equation 4, what I have is pi q dot and h, and then on the right side what I have capital P, capital Q dot, and the new Hamiltonian. Okay, but and then it depends upon q, p, and t. So this is delta f2 by delta t, and this delta f2 about delta q and q dot, and then delta f2 by delta p, and this is p dot. But here is some extra term is here. Okay, so that is my generating function. Here is some qpt minus qp. Why is there? Because if you see that in f2, if you write f2, what I'm going to get, if in f2 I'm going to get q dot capital P dot. Okay, from here if I this, so I'm going to a small q dot and capital Q dot. So in order to equate on the left hand side, I must have a small q dot and capital P dot. But originally what I have is a small q dot I have, but I have capital Q dot. Okay, in the expression. So from the generating function I have small q dot and capital P dot, but in my expression already, which is having a small q dot and capital Q dot. So what I want in place of this I want capital P dot. So if I add a term minus q p dot, so I'm going to have d dt of this. So if I take the d dt of this equation, so then I'm going to have q dot and p dot. So that is, first is if you keep p constant, then it becomes q dot, and if you give the q constant, and then you get the p dot. So in this way, this I have to get rid of this. Okay, and then I have to add this p. So then in this way, this earlier q dot is going to be cancelled with this q, and then I am introducing my p dot, so that I can take the common factor along with. So that's why this in this case f2, what I'm going to have is like minus q and p. This is transformation equation. So when you do that, multiplied by this, rearrange this dq and dp terms and dt terms, what you're going to get for this relation, this is these three relations, and then finally from there you get your transformation from q and p in terms of the small q, p, and t. Okay, so what is important that you need to remember, this is what is the f type 2 generating function, on which it depends, and what are the corresponding differential equation corresponding to generating function. Okay, so I'll stop it here up to till second type of generating function. In the next class I will cover up the two more f3 and f4 generating function, and try to do one more example, and then condition to find out that what is the condition to find out if you have been given certain transformation, then whether this transformation is canonical or not. So we're going to find out that in our next class. So for now I leave to this class. Thank you very much.